Hello, my name is Stefan Hodes. I'm a developer technology engineer working for AMD, and I'm going to talk to you about temporal upscaling, past, present, and future. Since we released Fidelity FX Super Resolution 2 last year, we have continually updated and improved the algorithm as developers integrated it into more and more games. Our latest version, FSR 2.2, was released just this February, and this presentation will not only give you insights in how the algorithm currently works, but I will go all the way back to our first steps into the upscaling territory and retrace our steps from those early beginnings to how we are today. Finally, FSR 3 has been announced last year, and while development is still going strong and it's too early to share any details, I will use this presentation as a chance to provide you with more insights in what we have planned for the new version and what we are currently working on. This presentation is structured in three parts. First, I'm going to talk about spatial upscaling FSR 1. I will talk about why we want upscaling at all and what problems you're facing when you're trying to do a spatial upscaler. Then I'll talk about how FSR 1 works and end on the note that you need a good anti-aliasing solution to pair with FSR 1 in order to get good results. This will then directly lead us to our temporal upscaling solution, FSR 2. Again, I'll talk about the problem space we're facing, which corner cases we detected during development, and go through the algorithm step by step and explain for every pass which problems it solves, how it works together with the other passes, and basically how FSR 2.2 works in detail. Finally, I'll talk a bit about FSR 3, which will add frame interpolation to the mix. And this adds a whole new set of problems, and I'll explain why we will need motion estimation to solve those and what other challenges we're currently concerned with. One final word, those three sections, you might be tempted to kind of correlate them to the past, present, and future from the title. But actually associating FSR 1 with the past doesn't do it justice, because FSR 1 is still a widely used and very popular library that many game developers use either for lower-end hardware or on mobile or handheld devices, or even just to give users a different option for upscaling if they want that. Why do we want to have upscaling in games in the first place? If you look back maybe 10 to 15 years ago, 720p resolution was the de facto standard for gaming. 720p has less than 1 million pixels per screen. This then significantly increased with 1080p resolution and 4K. And now we're even talking about 8K displays, which will have more than 33 million pixels, or to be precise, 36 times as many pixels as 720p resolution. Now, undoubtedly, with the higher resolution, the visual quality of the game significantly increased as well, due to being able to display smaller details and sharper edges, and overall they look much nicer. But also the processing power required to generate those frames has increased significantly. And if you look at the generated frames, then there are often cases where a lot of neighboring pixels are pretty similar, and there have been several techniques to leverage that and try to reduce the processing power, for example DRS or VRS. And the overall verdict of the games industry has been that we want to spend more time on the quality of the pixels than on the quantity, especially if we can reconstruct the quality by having a good upscaling algorithm, and that's basically where Fidelity FX Super Resolution comes in. When we started looking into building a spatial upscaler, it was clear that we needed to find a solution that works better than the filters most commonly used for upscaling, like point sampling, bilinear sampling, bicubic sampling, and length source sampling. On the right, you can see 4 images using those filters to upscale an image to higher resolution. And if you compare that to what you'd expect from an image rendered at higher resolution, then you will see that the edges are a bit more jagged than you would expect, and also all of the images are missing sharpness. So at the time we already had our Arcus sharpening library, and we thought if we can produce a filter that produces nicer edges than those solutions and then apply our sharpening, maybe we're in a good state and have a spatial upscaling solution that developers will actually like using. Also, our solution needed to be fast. It needed to provide an overall performance gain compared to rendering at higher resolution, obviously. We wanted it to be easy to integrate and open source and support multiple quality modes. And we did not want to be limited to certain hardware, certain driver, certain vendor, certain API by requiring some special features. So basically that's the corner points of our development. Let's start by looking at what we expect the upscaler to do. We want to be able to take any 2D input image without any restrictions, and then we want to output that image in a higher resolution. We want to improve the sharpness while retaining the edge information, and we definitely don't want to introduce any wrong color information, so we don't want to introduce ringing or so. We want the pixels of the output image to stay in the same color range as the input image, because otherwise further down the line, if the game does some additional post-processing after the upscale and assumes a certain color range, that could result in bad artifacts. So the problem is to find the geometry edge from looking at the input image alone. And if you get an aliased input image, as shown in the image on the right, we have two images showing the same input pattern caused by different edges in the game geometry. So the output we expect would be different, but we still need it to be temporally stable. So the better we can guess that edge, the higher quality our output will be. So what we do to reach that goal is, for every pixel, we analyze the region around that pixel and try to detect if we can find any features that we're looking for, like edges, where we detect edge strength and edge direction, or common shapes like corners. And then based on those features, we want to select a filter and apply that to the region around our pixel to generate the new output color for every upscaled pixel. So this sounds pretty much like you might expect from a machine learning algorithm. And actually, at the end of the development, that's what we have done. We used our algorithm and we implemented a machine learning algorithm, and then we compared the results of the machine learning to our algorithmic implementation and looked for areas where the machine learning actually did better, and then tried to figure out what features the machine learning tried to detect and what filter it applied there, and incorporate that in our formula. The reason why we did not use machine learning is simply because doing an algorithmic approach is much faster and requires less data and bandwidth. So in the bottom, you can see if you have a small local area that you analyze, in that case a 5x5 region. On the left you see a line that goes down 1 pixel every 2 pixels, and that can be detected pretty well and you get a nice straight line. But if the line is not as steep, like going up 1 pixel every 6 pixels only, then for 2 of the 6 pixels the algorithm will detect a perfectly horizontal line for 2 pixels, and for the remaining 4 pixels it will detect a line with a stronger increase than we actually have, so the line gets jagged. And so that's the problem we have with an aliased input. When we released FSR1, someone wrote, hey, it's just Lanxos, and I want to stress that it's not just Lanxos. So the documentation to FSR1 says it applies a directionally and anisotropically adaptive radial Lanxos. What does that mean? First of all, the Lanxos function is a filter function commonly used for resampling data and getting a nice and smooth result. And usually the result is a bit sharper than using spline interpolation or bicubic resampling. Now the radial Lanxos, if we apply the Lanxos in 2 dimensions and use the actual distance of a point to the sample location we want to sample and not the Manhattan distance, we get a radial Lanxos. And if we then detect some features and kind of squash that circle and rotate it to match that feature, we get our directionally and anisotropically adaptive radial Lanxos. Another change we made to the algorithm is that you can see the Lanxos function has some negative lobes which increase sharpness of the output image, and that is definitely desired. but we also want to make sure that the output image is in the same color range as the input image. For example, if the game uses a tone mapper and then an inverse tone mapping step after that and assumes that all colors range from 0 to 1, with 1 not being part of the image because that would basically break the reverse tone mapping step, then we need to stick to the same color range or we will get wrong colors and noticeable artifacts after that. So once we have applied our filter, we will clamp the output color to the expected color range of the input. And we're almost done with FSR1. So here you can see a comparison of the basic lang source upscale with our FSR1 upscale. On the left you can see lang source, on the right, especially if you look at the ring on the top, you can see that FSR1 produces a much nicer upscale result. And also on the high contrast edge of the archway next to the ring, you can see that by following the edge direction, FSR1 produces much nicer edges than basic lang source upscale. So we have it, our best-in-class spatial upscaling solution that we released in 2021. And it's very popular up to today, has been ported to many platforms and is still being used by a lot of developers. And on top of that, we have integrated it into our driver as Radeon Super Resolution, which will bring it to even more games without any special need for the developers to integrate it. I already mentioned the problems we have from receiving aliased input information, so it's not always easy to detect if there's a straight line or a curve, or if we have a curve versus a hard corner. And also we sometimes will introduce step artifacts if a line is not detected as having the same steepness for all pixels on that edge. Furthermore, we will generate temporal instability for slowly moving cameras or very thin objects which can be flickering from one frame to the other. So we recommend pairing our upscaling solution with a very good AA solution. On the right you can see two images, the same example I posted earlier, but this time with anti-aliased information, and you can see it's easier to detect which one is the straight line and which one is the curve. So there's three commonly used anti-aliasing solutions in games. First, there's super sample anti-aliasing, where you render the game first in a high resolution and then downscale it and then use our upscaler to upscale again. So it doesn't really make sense, right? The second one is MSAA. We've seen MSAA being used with our Fidelity FX Super Resolution 1 and it works quite well. But I would argue that if you already have like a high resolution image with MSAA and write your own resolve function instead of using the default resolve to low resolution and then upscale, you will probably be able to get a better result. And finally, most games already include a temporal upscaling solution, and we think this is pretty much the ideal solution. Now, if we suggest temporal upscaling to be paired with FSR1, then we should probably provide a temporal upscaling solution as well. And even better, we could combine our temporal upscaling solution with our upscaler and benefit from any synergies we have between those. And that directly led us to the development of FSR2. The goals or cornerstones we set ourselves when starting FSR2 development are pretty much similar to what we had with FSR1. There was a quality goal, like we wanted to have better visual quality than native rendering if the native rendering is done without any anti-aliasing. And we still wanted to achieve an overall performance gain because that's the main purpose of this library. Then we still wanted to have a very easy integration for developers, though it was clear from the start that it would be a bit more complex due to the additional requirements like camera jitter and motion vector data. And we wanted to make sure that the developer can retain full control over all resources and allocations, as the algorithm is obviously more complex than FSR1, which is just a single dispatch. Then for the quality modes, we wanted to add support for dynamic resolution scaling And of course, we still wanted to run on a wide range of hardware and not have any restrictions as to vendor or API or which hardware to run on. Now for this part of the presentation on the right, you can see basically a view of FSR2 with the different passes. The lighter two passes, Generate Reactive and RCAS, are optional passes, so they're special, and the main 5 passes of FSR2. And during the presentation, I will always highlight which pass we're currently talking about, because I'll jump around a bit during the presentation. It's just easier to understand how all passes work together if we don't go through the passes from top to bottom. The first thing you want to do when you start implementing a temporal anti-aliasing or temporal anti-aliasing upscale solution is to have a good camera jitter. So even if the camera doesn't move and the scene doesn't move, you want over time to accumulate different sample locations within your pixel to get you a nice anti-aliased result. The importance here is that the jitter sequence needs to have a good distribution over space and time. That means that the whole pixel area needs to be covered, and also you need the sample location to basically jump around your pixel pretty randomly. The most commonly used solution for that is the Halton 2-3 sequence, which we're also having an implementation for in FSR2 and recommend to be used, but you can apply any jitter sequence you like if you already have one in your game that works better. Now that we have our camera jitter defined, we want to talk about how to accumulate those samples to the final pixel color. You could simply say that each sample gets the same weight and gets accumulated to the pixel it lies in. But if you think about it, the closer a sample is to the edge of a pixel, the closer it is also to the pixel center of the neighboring pixels. So it makes sense to have the sample contribute to not only the pixel it lies in, but also to the neighboring pixels, and have the weight adjusted by the distance of the sample to the pixel center. And that's exactly what we do. Also on top of that, we want older samples to have lower contribution to the pixel color than more recent samples, because the most recent sample is obviously the most trustworthy. To do the resampling and weighting, we're using the length source function. Here I've plotted the mathematical definition of the length source function, and you can see there's that A value which can be used to control the sharpness. And you also see that the length source function contains 2 sine functions, 2 divisions, and several multiplications. So it's not really easy on the ALU, but it can also be implemented as a lookup table. So actually we've implemented both versions in FSR2, and always depending if the pass we want to use it in is ALU or memory bandwidth limited, we've exchanged the version of the function we're using. We've also included an approximate function that we found produces very good results, but we can't use in the reprojection step because that would cause noticeable artifacts. So let's add upsampling to the mix. So now for every low resolution pixel in each of the low resolution pixels, we have one new sample. We have multiple pixel centers of the high resolution image. Please note that the high resolution pixel centers will not always align nicely with the low resolution image, as we want to support dynamic resolution scaling or just any arbitrary upscale ratio. So for computing every pixel in the high resolution image, we will look at the 4 samples that are surrounding this pixel and weigh them with the length source function. And for that we will modify the length source function with a beta value, which is based on the temporal stability we detect for that region of the screen. And then we will accumulate all those color values and weigh them with the length source weight and accumulate the length source weight, and then use that to normalize the pixel color as usually done with filters. And you should also note that it is possible for that summed up weight omega to be negative for some pixels, which will be relevant in the next step. So the final color we compute is then a blend between the history color and the current pixel color, and you might recognize the normal alpha blending function here, the linear interpolation, where the alpha value used is the max of the weight and null. So basically we're clamping it at 0 to not have any negative contributions if basically the current pixel color is negative or we don't trust it at all, divided by the trust we have in the history of the pixel. So the history trust is determined by if the pixel was disoccluded, if the velocity is matching the current velocity we're seeing, or if there have been any shading change. And that concludes basically our accumulation. So I've said we're done with accumulation because we're accumulating and we're upscaling, but are we done yet? Not quite. There's snowflakes. So this screenshot is from Deathloop by Arcane Studios, and it shows a very early integration of FSR2 into the game. And we noticed that FSR2 causes very heavy ghosting on the snowflakes. So the artifacts seen in the screenshot are purely to blame on the FSR2 team, not on Arcane. And we're very thankful for Arcane to let us use this screenshot. Anyway, the colleague who was tasked with fixing the snow ghosting had a very hard time because there's large snowflakes, small snowflakes, some have very hard outlines, some have soft outlines, some are moving in straight lines, some are moving pretty randomly. It was very hard to detect which pixels actually belong to snow. And on top of that, half the background is snow. So when he managed to fix this, he said he never wanted to see a single snowflake again in his life. Unfortunately for him, he's living in Sweden, so good luck with that. On top of that, there's other problems like translucent objects, reflections, animated textures. We haven't dealt with changing light conditions yet, nor have we with moving objects or a moving camera. We just accumulated pixel samples. So if your game looks anything like Minesweeper, we're good. Otherwise, we will have to invest some more effort and find out if the history data is actually trustworthy. So jokes aside, if you look at the leftmost image here, that's where we currently are with just accumulation. If we have moving objects, you basically get a blurry mess. So the next thing we want to do is ask the developers to provide a 2D motion vector map. So basically a map that tells us for every pixel where the object that resulted in that pixel has been in the previous frame, so we can correctly map that. I want to note that this motion vector map should not contain motion due to camera jitter. So basically for objects that are standing still, we're expecting null motion vectors. So now we can follow the objects correctly, and the result of that is what we see in the rightmost picture. We still see a lot of ghosting, but the object itself is nice and sharp, and so is the background where no object has been moving about. And the rest of the FSR2 algorithm will basically deal with removing that ghosting. Now, where does that ghosting come from? If you look closely at the image and look at a part of the moving objects, then you can see two images, previous frame and current frame, where the object has slightly moved. And if we overlay the motion vector map, then we can see we have motion for the moving object. And if we follow the vector from one pixel to the previous frame, we see we get the corresponding pixel and nice sharp object in the resulting frame. But if we follow the motion vector of a pixel that does not contain the object anymore, but basically has been disoccluded, as highlighted in the frame now, we will end up on a pixel that in the previous frame still contained the object that has moved away. So basically we want to determine which pixels have been disoccluded, so we don't use the history for those pixels. And that will happen in the reconstruct previous depth pass and depth clip pass, which I'll be talking about next. To figure out if a pixel has been disoccluded, what we're doing is we take the current depth buffer and reproject it to where it has been in the previous frame. In the example on the right, you can see that the camera is moving slightly forward, so every pixel is slightly more towards the middle of the screen in the previous frame. Now, since a reprojected pixel will hardly ever land exactly on a sample location or the middle of a pixel, we will distribute that pixel to all 4 pixels it lands in between. That way we're being a bit conservative. And when we write the depth value to those 4 pixels, we're using an atomic min operation. So if multiple pixels land on the same pixel, then we just keep the closest one and the other ones are discarded. Other things this pass does is we dilate depth and motion vectors to be conservative. And finally, we compute the luma value that we're using for the log as an input, basically to track later if the luma has changed for the logs. So now we have our disocclusion mask and we can apply that to the accumulate pass to remove some ghosting, but that only will work for pixels that actually write the depth buffer. For the remaining ghosting or pixels that don't write depth, we need a different technique, and that's the color rectification. So how that works is we take our low-res image from the current frame and will build a color bounding box out of the information of the current pixel and the surrounding pixels. And then we will compare the color value of the history pixel that we reprojected and want to blend with the current sample to check if the history color is basically reasonable. Like if it's within the bounding box, we accept it. If it's outside the bounding box, we clamp it to more closely match what we expect the colors to be from the current rendering. So this will fix changing light conditions, moving shadows, but also particles moving away, all that kind of stuff. The problem with color clamp is with thin features. Those can be either geometry based or just features in some texture somewhere. Thin features are features that are smaller than 1 pixel, so as a result, with the camera jitter, they will not appear in every pixel or every frame for that pixel. As a result, the color rectification might decide this feature seems out of place and will tune down the influence of the history, resulting in a dimmed down and temporarily unstable feature. And we don't want that. So basically what we want to do next is to lock pixels belonging to those thin features. So color rectification is not applied to those. So the thin feature will appear strong and stable as seen in the rightmost image here. The way the log pass works is as follows. We analyze a 3x3 region of pixels and try to determine if the middle sample is part of a thin feature. To do that, we analyze the luminance of the pixel and compare it to the luminance of the surrounding pixels and check if the luminance of the surrounding pixels is similar to the one of the middle pixel. Then we mark those pixels where the luminance is similar and check if we find any 2x2 square of pixels with similar luminance. And if that's not the case, then we assume the middle pixel is part of a thin feature. So in the example below, you can see that for the upper 3 examples, we assume a thin feature, and for the lower 2 examples, we assume the middle pixel is part of a either thicker line or the corner pixel of a larger feature and will not be marked. Now that we have a mechanism to generate logs to preserve thin features, we want a way to unlock them as well. So first of all, the logs get reprojected with the motion vectors to keep track of the location of the logs. and the locks will decay over time. So after a certain time, if the lock is not being refreshed, it will disappear automatically. And then there's some manual ways to remove locks. First of all, if an object is being occluded and then disoccluded, obviously the lock will disappear. And we check if the shading around a lock changes significantly over time. If that happens, we assume that the lock is not current anymore. Then there's the reactive NTC masks. If those are applied, this can kill the locks as well. And finally, in version 2.2, we have added that spatial or temporal motion divergence. So basically, if the motion vectors are too large and too divergent, then this can result in locks being removed. Now we're only missing one more pass for our core algorithm, which is SPD. SPD is the FidelityFX single pass downsampler, which we're using to downsample the luminance of our input image, and we're writing out MIP4 and 5 of that to detect if the average luminance around a pixel has changed, which will then assume that the shading has changed and will use to unlock pixels. And then we'll continue downsampling until we only have one average luma value for the whole scene, which will then be used for the auto exposure in the prepare input color pass. In the two screenshots on this slide, you can see the effect of the reactive NTC masks. On the left is a screenshot from a scene specifically designed to highlight ghosting artifacts that might be caused by the core algorithm. And on the right, you see the same scene with the reactive NTC mask being applied. So the particle effect in the background has a lot of ghosting and the fast moving particles almost disappear. And the balloons moving up and down cause locks to stay on screen and thus objects behind the balloons staying visible. So while the automatic generation might be helpful for integration of the technique into your game, if you have the ability to specify the reactive and TC masks directly, that is likely to produce even better results than the automatic mask generation. Obviously, if you want to provide those masks yourself, you need to know what they are about. So the reactive mask is a mask that marks pixels to reduce the influence of the history. So basically it influences the alpha value in the blend between the history and the current sample intensity directly. Values should be significantly below 1, otherwise this will cause temporal instability as the camera jitter will become visible. This is very helpful for small particles, highly reflective surfaces, and animated textures. The texture and composition mask is a mask that will reduce the lifetime of locks. So this can be used for larger translucent objects, also for reflections and animated textures. This concludes the part about FSR2. I haven't mentioned RCAS yet, but that's just an optional pass of our sharpening filter that can be applied to the final image to get an even sharper and more crisp output. Now with FSR2, we are already computing more pixels than we have samples for the current frame. And we were wondering, can we maybe apply the same reprojection and blending magic that we use for FSR2 to generate completely new interpolated frames and thus double the frame rate and make the games run even smoother? Now things are never quite as easy as you first think, and the biggest problem we encountered is that we can't use color rectification anymore. The reason for that is that we don't have a ground truth image, be it at low resolution, for the time where we want to generate an image for. Also, we only have linear motion interpolation available, since the motion vectors we get provided by the game developers are just linear in 2D space. And finally, if we want to generate new frames completely, we have to interpolate everything, including post-processing and UI. The good news, on the other hand, is that there's a high probability we will have at least one sample for every interpolated pixel, either in the previous or in the next frame. And we won't have such a big problem of ghosting. We don't have a feedback loop. because every interpolated image will be only shown once and then be thrown away. So the problem of ghosting is a lot less prominent than it was with FSR2. Now let's take a look at how FSR3 will affect the frame structure. This graph shows an abstract view of the frame. There's some rendering, some post-processing, some finishing touches like UI rendering, and finally the frame gets presented before preparation of the next frame starts. This graph does not show CPU and GPU workloads happening in parallel, the CPU possibly using multi-threading and the GPU possibly using multiple queues. So it's a very simplified view, but it will suffice for what I want to show here. When we add FSR2, the rendering portion of the frame will use a lower resolution, and as a result the performance significantly improves. Then FSR2 adds an upscale pass, and everything after that, post-processing, UI rendering and the present, are not affected by FSR2 in any way. Overall, you can see the frame got significantly faster, the frame rate improved, and so has latency. With FidelityFX Super Resolution 3, in addition to what we did with FSR2, instead of directly presenting the frame, we add an interpolation pass and present the interpolated frame first. The real frame will then get presented roughly in the middle of the next frame. Overall, FSR3 will improve frame rate and smoothness of animation significantly. Latency, however, will be slightly increased compared to FSR2, though it should still be better than native rendering in most cases. Also, the interpolated frame will already contain some reaction to the user input, so we expect while the latency to the present of the real frame is increased, the impact to latency perceived by the user should be similar to FSR2. The cornerstones of FSR3 development are that first of all we want to double performance compared to FSR2. We also want to add latency reduction methods so developers can claw back some of the latency they will lose from the real frame present being delayed for half a frame. Then we want to ensure that FSR2 to FSR3 transition is as easy as possible. And finally, we're committed to release the FSR3 SDK under a permissive license as open source, similar to everything else we released under the FidelityFX SDK. So while I can't go into details yet how FSR3 works, I already mentioned that we can't rely on color clamp to fix any artifacts from objects that don't write depth or motion vectors. So instead of the color clamp, we will rely on a second set of motion vectors generated by AMD Fluid Motion technology, and then use some estimation which set of motion vectors, the game-provided motion vectors or the generated motion vectors, produce a better result to be basically which pair of pixels is more trustworthy to generate the final interpolated image. So good motion estimation is key for this interpolation, otherwise especially transparent objects or shadows won't work correctly. But apart from that, additional information from FSR2 can be leveraged, so basically good upscaling will result in good frame interpolation. Then I already mentioned another focus area of FSR3 is the latency reduction. So basically since the 90s we always try to push back the frame rate barrier and increase the frame rate of games. And I think with frame interpolation this frame rate barrier will actually vanish, and like it is with development, there always comes a different bottleneck, and I think the next bottleneck we will encounter is frame latency or input latency, and we as a game development community will have to work on how we can get this latency as low as possible for the best gaming experience. And the solution for that might be different for every game, but we will try in the FidelityFX SDK to provide a good solution to help developers to attack this problem. Finally, we want to have FSR2 integrations be easy to transition to FSR3, and of course we will release everything under the MIT license. Now we've certainly come a long way since we first started looking into upscaling technology. We went from spatial upscaling to temporal upscaling, now we're adding frame interpolation to the mix. And all this represents years, if not decades, of R&D innovation. I have shown with this presentation that it always has been an iterative process, and I hope I've let you retrace some of the steps to see how we got where we are today. Some challenges certainly remain, but I'm looking forward to the next step of the journey, with FSR 3 being the next step of evolution of Fidelity FX super resolution technology. It will allow gamers to experience smoother gaming while at the same time allowing developers to focus more of their GPU time on visual quality instead of just rendering more and more pixels. So I hope you liked this presentation and wish you all a very nice day. Thank you.